Welcome, everyone. Well, good evening, and welcome to the public lecture hosted by KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology. My name is Sinan Du. I am the Outreach and Engagement Manager here at KIPAC, and I will also be your main host tonight. Well, it's wonderful to see all of you in person, especially in our new location, simply because our default room has an out of order projector. So we cannot use that this time, but we're hoping to go back to that room sometime in 2026. And we also welcome the online audience of a similar size who is currently watching the live stream. So welcome. Well, if you have followed KIPAC public lectures for a little bit, you may know that we try to feature topics that you would like to hear about. And tonight's topic is actually selected that way. And we thought it might be a good idea to have this talk before the end of the year, just because it's still timely and relevant to the 2025 Nobel Prize in Physics. So tonight's talk will be focused more on the technology side. And Chelsea, our speaker, will also be sharing a little bit how we're taking advantage of the emerging quantum technology to search for dark matter. So before we start, I would like to give a big shout out to the entire team supporting this event tonight. So these include the front desk staff, some of you may have already interacted with. We also have the AV team here. We have Leon, who is managing the live stream. And because this is also a hybrid event, we also have online chat moderators who are subject matter experts who is answering questions online. So I will give them a chance to say a quick hi before we get started. All right, so first we have Andrew.
All right. Hi, I'm Andrew. I am a postdoc and I'm working with Chelsea. I've been doing dark matter research for quite a while now and naturally had to also delve into the quantum related stuff as well for my research. And I am excited to be here and to chat with everyone.
Great, thank you. Next we have Pam.
Hey everyone, I'm Pam. I'm a third-year PhD student here, also working with Chelsea. My research focuses on quantum devices for application, these Axion searches that you're going to hear about, and specifically I work on the DM radio collaboration. So I'm excited to be here with you today.
Awesome. And last but not least, we have Barkotel.
Hi, I'm Barkotel, also working with Chelsea. I'm a second-year physics PhD student working on both the high-frequency ADMX experiment and low-frequency DM radio experiment. So excited to be here as well.
Great, thank you all. And all of you will also be hearing more about what those experiments are actually about during this talk. So for those of you joining online, you are more than welcome to use the live chat box on your right-hand side to ask any questions you have and also engage in discussions. Most of the questions, online questions, will be answered directly by the chat moderator, and the remaining one will be addressed by Chelsea at the end of the talk. And for all of you joining us here in person, please save your questions until the Q&A. And Chelsea is here in this room until all the questions is answered and in person. All right, so now it's my greatest pleasure to introduce tonight's speaker, Dr. Chelsea Bartram. Chelsea is an experimental particle physicist working at SLAC at Panofsky, where she also leads her own group. Chelsea grew up in Ohio, where thunderstorms are very common. And it was actually the dramatic phenomenon of electromagnetism typically seen in those thunderstorms that initially inspired Chelsea and got her interested in all forms of light, including light that we cannot see, such as radio waves. For many years, Chelsea held on to that passion, and that's how she first pursued a bachelor's degree in physics at Boston University, where she also got to work, do research with the Large Hadron Collider in Switzerland. Afterwards, she got her PhD from the University of North Carolina at Chapel Hill, after which she pursued a postdoc appointment at the University of Washington before joining SLAC. So, you know, Chelsea in the most recent years has returned to her early love for electromagnetism through the search of Axion Dark Matter, which you will also hear more about today. And she's very excited to share with us the search of such dark matter particles using both the old and the new technologies, including radio and quantum sensing. So without further ado, let's give it Chelsea a round of applause.
Okay. Thanks everyone for coming here today. The title of my talk, as Zenon said, is Quantum Sense, addressed to the inhabitants of the universe on the topic of dark matter. Now, you might be thinking, what a strange title that is. And you would be correct, I made that up. But it's a reference to the pamphlet called Common Sense, which was the best-selling text in early American history. I wanted to speak to this idea that Common Sense promoted, which was that we live in a democracy and it's super important to make sure that the public is informed and knowing how science and other fields are being done. So in the spirit of democracy and revolution, I will now tell you how quantum sensing is revolutionizing physics. And so the big news that came out recently was regarding the Nobel Prize in Physics. And the prize was awarded for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. And so it was awarded to these three folks here, John Clark, Michel Devereux, and John Martinez. And it just so happens that one of our collaborators is shown here on this slide. So John Clark is a collaborator in dark matter searches that are ongoing at both Stanford University and SLAC. And so back to the title slide, quantum sense, I want to point out, is actually not common sense. And so to illustrate this, I want you to imagine you're hiking and you need to cross a mountainous barrier. So this was something I did every now and then as a postdoc here at the University of Washington. And you can imagine that here you are. Here's an example, a local example on Half Dome. And if you're on one side, you cannot just appear on the other side. It actually requires energy and effort to cross over the mountain. So common sense says, if I don't have the energy to fight gravity, I am stuck. And so there's me still camped out on one side of Half Dome. Quantum sense, however, says that there is actually a small chance I will just appear on the other side of the barrier. So there's me suddenly on the other side of Half Dome. Okay, and we all know this doesn't usually happen. So this doesn't happen for macroscopic objects. And so what does quantum sense actually mean? Quantum sense applies to very, very small particles. And so it works on a microscopic level. So conventionally, with macroscopic objects, we know that items cannot physically appear on the other side of the barrier unless they have the energy to go over the barrier. Microscopically, if we're talking about fundamental particles, such as the electron, there's actually a finite probability that the electron will appear on the other side of the barrier. Now, that probability is very, very small, but this is due to quantum mechanics. So quantum mechanics tells us that there's some probability that the particle can appear on the other side of the barrier. And we tend to describe this with a wave-like description, which we call the wave function. And so why is this useful? It has been useful in a variety of fields. For example, the description of radioactive decay. And so you can see here, this is a parent nuclei decaying into two daughter nuclei. And it just so happens that tunneling is an accurate description of this behavior. So the phenomenon I just described, wherein there's some probability that the particle escapes a barrier, although it does not have the energy to overcome that barrier. And so this was essential for helping to understand radioactive decay and additionally solar fusion. And so we've had great success understanding a variety of phenomena by understanding this phenomena of quantum tunneling. So then there's this bigger question, literally, which is, can it describe macroscopic objects? And for a long time, the answer was no. So in fact, there was a joke about this, and maybe people aren't aware if it was a joke, but there's this story called Schrodinger's cat. And the story with Schrodinger's cat is that you have a cat in a box, and the box has a radioactive component to it. So that's depicted in this box here. And that radioactive element decays, or it does not. And there's some quantum mechanical probability that it either decays or it doesn't. And the cat is therefore either dead or alive. So the cat is dead or alive, and we don't know for a fact if it's dead or alive until we open a box and make a measurement. So that is what is shown here on the right-hand side. And so this is Schrodinger's cat. You know, I happen to love cats. I actually have one myself. So I just want to emphasize no cats were harmed in the making of this talk. So this is Saturn sitting in her box, alive. And so this illustration was to show how farcical it is to think that quantum mechanical behavior could apply to macroscopic objects or people or cats. So we tend not to think about quantum behavior when we're thinking about our everyday life. So back to the Nobel Prize and the topic it was awarded for. We go back to the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. And I inserted a word here called superconducting because that is crucial to observing this phenomenon. So how does tunneling relate to superconducting circuits? So how does superconductivity work? Let's start there. And so the first top illustration shows electrons in a normal wire moving individually. So this is what we know as an electric current, right? But then if we think about superconducting current, you'll have electrons pairing up in what we call Cooper pairs. And it just so happens that this is sort of the lowest energy state for them to occupy, and then they can move with no resistance. So that's the definition of a superconductor, is that you have current flowing with no resistance. And it just so happens that this phenomenon only appears at sufficiently low temperatures. So typically when you hear about superconductors, that means that these circuits are operating at extremely cold temperatures. And the reason why this is interesting is because this is a good environment to isolate and observe quantum mechanical effects, because there is less motion and therefore less contact with the environment. So how does tunneling relate to this? You can suppose there is some non-conducting, or we say insulating, barrier in the superconducting wire. So then the question is, can these so-called Cooper pairs cross it? And it turns out that they can. They can tunnel, like we talked about. In fact, the Cooper pairs can act in unison as a single wave function in spite of this barrier. In addition, we have this term called phi, or the phase, and this quantifies the difference in the wave function on either side of the barrier. So this is crucial to understanding superconductivity, and it is also critical to explaining this phenomenon of macroscopic quantum tunneling. So that connected this very small effect, the quantum effect, to a more macroscopic effect, which was to say an electric current. Okay, an electric current is a more macroscopic effect because you have all of these electrons acting in unison. Now, there was a second element to the Nobel Prize, which was this notion that you can have energy quantization in an electric circuit. And so the idea was to basically send in a microwave photon or light particle, and that provides some energy, and there are sort of discrete energy states, energetic states of this wave function, and that sort of determines the behavior of the circuit. And so these two key sort of observations, the macroscopic quantum tunneling, in addition to energy quantization of an electric circuit, were sort of the big news that were celebrated by this Nobel Prize. Okay, so what? What do we do now? Well, it turns out you can build some pretty exciting devices using this technology. So there's something called a superconducting quantum interference device, or a SQUID, that uses these Josephson junctions. And so I want to go to the figure here on the right. So this is the schematic symbol for a SQUID. And you can see there are two Josephson junctions indicated by the X on either side. So that's the configuration of the circuit. And this, it turns out, can actually detect magnetic fields of 5 × 10⁻18 Tesla, which is 1 trillion times smaller than Earth's magnetic field. So this is pretty incredible stuff. And so there's been a proliferation because of this of various quantum devices. And superconducting Josephson junctions and superconducting materials are the building blocks of quantum sensors and amplifiers. And quantum amplifiers can boost the signal strength while adding minimal noise. This requires some sophisticated nanofabrication techniques, and Stanford and SLAC do a variety of device fab all here in-house. So it's a great place to be for quantum sensing. And you can see, in fact, over here in the image, this is actually an image of a quantum sensor built at SLAC in Stanford. So amplifiers help us build very sensitive radios. If you connect a radio to a quantum amplifier, you can detect extremely small signals. For example, you can detect signals on the order of 10 to the minus 23 watts. And so this would be the same as having a phone on Mars that gets 4 bars of cell service. So that's a really great radio. In fact, I think we can now make a recommendation here to Matt Damon in The Martian. Okay, so just a quick reminder, because some folks in the audience might be sort of younger. What is a radio? This is slightly older. I'm sorry. The radios allow you to detect electromagnetic waves. I know maybe I'm dating myself. That carry information like music or news. It used to be common in your living room, but got replaced by TVs. Your cell phone is actually a sophisticated radio, as are walkie-talkies. And there's often a radio in your car. So here are a few radios that are owned by me. And then the question is, how do you build a radio? Well, there are 3 electrical components that are essential. These are capacitors and inductors. And then you'll often see a resistor, which you can't avoid because every electrical component has some. And basically, the capacitor stores electric field energy, whereas the inductor stores magnetic field energy. And the energy storage oscillates between the two. So here you can see a depiction of this, this radio oscillating at a particular frequency. And you can see sort of here is the signal as a function of time. So we call this the time domain. And then you can calculate what is the resonant frequency. That is the frequency it's going to pick up the best signal. And this is given by this equation here, 1 over square root of the inductance times the capacitance. So if you change these values of L and C, you can tune your sensitivity to a different frequency. And so here we go. I'm tuning. I'm changing the values of L and C. Now they're orange. And we're going to different frequencies. So you can see this is a higher frequency now. So that was the time domain. Now we're going to shift to thinking in terms of frequency. So you can see on this plot, this is showing the frequency of the radio as it tunes. And then this is showing as that you can extract from whatever signal you're interested in. And so as you tune the dial on your radio, you're basically changing that resonant frequency. And you can see that move as so. Okay, so that brings me to my next question, which is why build these radios in the first place? Well, 1, it's fun. 2, there are lots of interesting physics possibilities. And 3 is going to be the rest of the focus of my talk, which is dark matter detection. And so I'm not going to go in depth about the existence of dark matter. We have had former KIPAC hosted talks on this topic, but I will mention the key details here. So dark matter is a form of matter that makes up 85% of the universe, and we don't know what it is. We have evidence that it exists. We call it indirect evidence from astrophysical observations, such as stellar motion in the Coma cluster and the rotation curves of galaxies. At this point, there's actually a huge abundance of evidence showing that dark matter exists, but we don't know what it is precisely. So the question is, can we find direct evidence, i.e. a signal that is arising directly from the dark matter? And it turns out that we can, we think. So I'm interested in a particular candidate called Axion Dark Matter. And it turns out that the axion turns into a photon or a light particle in a magnetic field. And so there are two key parameters associated with this interaction. The first is a term called GA gamma gamma. So you'll see this on our plots. This represents sort of the likelihood or the strength of the interaction. It has these sort of funny units of 1 over GeV. So this is sort of an energy, GeV is an energy unit. And then the second key parameter here is the mass of the axion. And so this has units of EV, or electron volts. So this is just a diagram showing the interaction where an axion turns into the photon in a magnetic field. Okay, at what frequencies, though, do we build our radio? Well, it turns out the frequency of that light signal is possibly quite wide. So we don't know exactly what frequency the signal will occur at, but we have sort of this idea that there's a very broad range. So the lower bound here is set by the dark matter halo size of dwarf galaxies, whereas the upper bound is set by, oops, over here, supernova 1987A and white dwarf cooling time. So these sort of bound the range over which we want to look. But you can see here that the frequencies we're looking at are over a very wide range. And this is very low mass for any particle. And so just for perspective, 1 EV, so this is 10 to the minus 2 EV, 1 EV would be around here, and that's 10 to the minus 36 kilograms. Okay, so where do we look? Well, we like to reference a plot called the perimeter space plot. And so there's two important axes to reference on here. The first is the x-axis, which is the axion mass. And so just going back to what I just said, this is in electron volts, or EV. And again, for perspective, the mass of the electron is actually way off the chart to the right. So the mass of the electron is about 500 keV, so quite large by comparison. And then the y-axis shown here is the axion interaction strength. And so again, this is showing how strongly the axion couples to that particular interaction. Okay, so where have we looked throughout this space? We've looked in all of the gray regions shown here. And so you'll notice that most of these are at the top of the plot, right? And that's because that is the sort of easiest region to detect. There's also this yellow band. And the yellow band represents a particular form of the axion called the QCD axion. And the QCD axion solves an important problem in nuclear physics, which is called the strong CP problem. And it can account for all of the dark matter. So this is a very compelling model of the axion. I won't go in depth on the topic of the QCD axion, as this is more of a detector-based talk, but it is truly a compelling model. And in fact, we have some connection to the development of this model at SLAC via this theorist, Helen Quinn. So Helen was a SLAC theorist who predicted something called the Pesce-Quinn mechanism, which predicted this QCD axion. Okay, so ultimately, we are really interested in this yellow band. So the question is, how do we detect signals that would be in that region? And ultimately, we require quantum sensing to achieve sensitivity to this QCD axion. So you might notice from this plot that there are not there is not much gray area in the yellow region, and that's because it is very challenging to get there. And so let's talk about this particular result, which came from one of my experiments that I work on called the Axion Dark Matter experiment. So this is the Axion Dark Matter collaboration. We go by just ADMX. You can see it consists of a variety of different institutions that are both sort of domestic and international, shown here. And this is a photograph from our recent collaboration meeting, one of our recent collaboration meetings at the University of Washington in Seattle. So this is what the ADMX experiment looks like. This is a photograph from National Geographic, and it's showing basically the sort of radio that we use to detect the dark matter. And you might think that doesn't look much like a radio, and you're right. But it does look a bit like a metal coffee can. So it's a big cylinder made of metal, and it does have intrinsic inductance and capacitance like we talked about. So it works as a radio. So here's sort of a cutaway drawing of this experiment. So you can see that there's this, we call it a cavity, a metal cavity, sitting inside a magnet. And the magnet we use is very high field. It's about 8 Tesla. So this is comparable to MRI magnets that you might see in a hospital. And the axion is expected to come in here, interact in the magnetic field to create a photon or electromagnetic signal. And then that signal will get picked up by a wire probe that sticks into the cavity, and it propagates to our quantum amplifiers shown here. And so those quantum amplifiers, again, are critical to achieving a high signal to noise. And then the signal comes out of the detector and gets turned into this power spectrum shown here. And so the power spectrum shows the signal to noise as a function of the frequency. And if you see an axion, you would see a peak that looks something like this, okay? And so that peak is occurring at a particular frequency, and you can convert that to a particular mass. And that will tell you what the mass of the axion is. Now, I want to note before I keep going that all of this has to be extremely cold because we need to suppress our noise as low as possible. And so you'll also see this label called dilution refrigerator shown here. That's how we make things cold. Another item to note is that we do not know the mass of the axion a priori, and so we have to actually tune our resonator. And so here you can see 2 tuning rods. They're sort of these cylinder tubes running the length of the cavity, and we just move those continuously throughout data taking to tune that dial on our radio. So here are some great pictures from Seattle. You can see on the left, this is showing what we call a rigging operation. So this is the procedure by which we sort of bottle up the detector. We put on all of these shields, and then we put it in our magnet, which is shown on the right here. So this is looking down into the magnet, which is in the ground. And you can see there's some gas coming out of it. That's from the liquid nitrogen, because it's also very cold. And so ADMX recently achieved these results shown here. So again, this is that plot that I showed you before. This is that GA gamma gamma, the coupling strength, versus the mass or the frequency. And you can see that the purple is where we looked, and we unfortunately did not find anything yet. So if you're curious about this result, this was the name of the paper. And no axions were found, but the search continues. Now I'm going to change gears here and go to another experiment, which is called DM radio. And so this experiment is actually physically located here at Stanford University. You can see this is a recent picture from one of our collaboration meetings. And it consists also of a variety of institutions. I believe all of these are domestic, and these are our funding agencies. Now, DM radio looks more like a traditional radio schematic that I showed you earlier. You basically have your magnetic field. You have your tunable radio here, and then you have your quantum sensor. So this is your squid. But in real life, it's a little bit more complicated. So this is what the geometry looks like. we use a toroidal magnet, which looks like a donut, and create a magnetic field of about 1 Tesla. That creates the AC electromagnetic signal when the axion interacts. In turn, that creates an AC magnetic flux that gets picked up by our radio. So here you can see this is the inductor part of the radio, and it's picking up that signal. And then finally, we read that out using a squid. And so again, we have our power spectra as a function of frequency, and we're looking for that peak. So what does the DM radio resonator look like? Again, it looks more like a conventional radio. Here you can see this is a photograph of an inductor wound out of superconducting wire from one of our collaborators at Princeton. And then we also have a capacitor shown here. And a key figure of merit for us is something called the Q factor, which is a measurement of the sensitivity of the resonator. So if you have a high Q factor, you have a really sensitive resonator. And our collaborators recently achieved a Q factor of 2.5 million at 250 kilohertz. So that was very exciting. We also require this toroidal magnet. And so this has been a joint effort with a company in Boston called Superconducting Systems, Inc. We had a lot of design work that was done by the Stanford graduate students and postdocs. And so you can see one of their CAD drawings shown here. And then we've communicated with the company, and they've actually built and constructed the magnet shown in this photograph, and they're currently in the process of testing it in Boston. And so what do we aim to do with DM radio? We want to search in this region of the parameter space plot. So this yellow region. So this covers this mass range, which is 20 PeV to 20 nano EV. And that corresponds to frequencies of 5 kilohertz to 5 megahertz. One of the key features of DM radio is that we want to use this as a quantum sensing testbed. So we're going to deploy the sensors that I've been talking about, such as squids, in addition to some other more sophisticated sensors that can let us achieve even lower noise to really push the sensitivity to go beyond what we initially predict with this experiment. And so the goal is to basically develop that technology that we need to reach this GCD axion band. And so we're at a very exciting time for this experiment. We're actually commissioning right now at Stanford University. And so on that note, I want to show you a little bit of what this looks like. So this is a time lapse taken by one of my students. And you can see this is everyone assembling the cryostat for DM radio. It's got multiple layers of shielding, and that's sort of to lower the temperature incrementally from room temperature down to that cold base temperature. And so you can see particle physics is a really collaborative effort these days. You need to be able to communicate with all your coworkers really effectively and work as a very coherent team. So here you can see that outermost shell going on. Okay, so in my last few minutes of this talk, I want to transition and talk about what happens if we actually find something. So let's go back to that power spectrum. In the case of the ADMX experiment, this might be at higher frequencies. In the case of the DM radio experiment, this might be at lower frequencies. But let's zoom in on that peak, because that's what we would see in the event of an axion signal. So if we zoom in, it turns out it's a bit more complicated than a single peak. It actually has what we call a line shape, which looks something like this. And you'll see that if you sit on it for a long enough period of time, the frequency will actually shift ever so slightly. So we call that the Doppler effect. And it's the same idea as when you're standing next to a train and you hear the shift in frequency go by when it's blaring its horn. And so the idea is that we're actually moving relative to the dark matter. So the dark matter is all around us. And as we move through the galaxy on Earth and we spin on axis and rotate around the sun, we are moving through the dark matter. And so there's going to be this slight shift in the frequency of the signal. And so that's what you're seeing here. And so presumably, if we can use this to really confirm that it is the dark matter that we're seeing and that we understand it. And so that brings me to sort of my big picture, which is at KIPAC, we're interested in astrophysics more broadly. And you might have heard of some of the other endeavors going on here, such as the Vera Rubin work at the Vera Rubin Observatory and LSST. So a signal detection of the axion would tell us about the dark matter, but it would also tell us more broadly about other astrophysical phenomena. For example, it impacts galaxy structure, large-scale structure, galaxy formation, gravitational lensing, CMB mapping, and more. Additionally, quantum technologies obviously play a role in this experiment, but also they play a role in other efforts. So there's a lot of synergy in terms of the technology going on here at KIPAC, and how can we best use that technology to sort of do as much science as we can. Okay, so in conclusion, quantum sensing has enabled dark matter searches that were never previously possible. It's gotten us sensitivity to that QCD axion band. Radios can be used to search for the dark matter in sort of new and exciting ways, and a discovery is possible at any moment. And so I just encourage all of you to chill out and stay tuned. Thank you.
Great. Thank you very much for this very informative talk, Chelsea. I know we have probably a lot of things to unpack here, but we will have plenty of time to actually take the Q&A. So we'll probably start with the in-person audience. Feel free to just raise your hand. Yes, and I will repeat the question for our online audience. Okay, right here.
Yeah.
Okay, so yeah, the question is there anything else, say like other particles that could give the same signal that axion probably would give us?
Okay, yeah, that's a great question. And it's true. However, actually, most of our the sort of fake signals don't come from the category of other particles. They come from sort of ambient radio signals. Yeah, so actually, funny story with the ADMX experiment, there was a nearby radio station and we thought we had an interesting signal, and then we traced it back to a local station. So you have to really do your homework and understand the ambient environment and make sure. Yeah, so it's really cool because you can actually, if you wanted to demodulate the signal, this is another word for you take the signal and you turn it into the audio, so you can put it in your earbud and hear that what the signal is. And so you could listen to the axion, literally, if you want.
The QCD axion. So the question is, if we remember the plot where it shows the axion mass and also the axion interacting strength. So there's that band which signifies where QCD axion would behave. So is that like where you would expect to find all the axions?
Yeah, that's another great question. So it depends on what theorist you ask, but I think so. There are sort of some assumptions baked into that plot about what the local dark matter density is. So the dark matter has a particular density around us. And so you have to kind of account for that. And it's not necessarily the case that all of the dark matter would be, the QCD axion. It can make up all of the dark matter for sure, which is compelling, but there might be other components of the dark matter that we don't know about.
Great. Question over there. Great question. So the question was, how are you, or like, how would AI be helpful in terms of like searching for axion dark matter, like in your line of work?
Yeah. So one can try to better understand the noise, for example. So the noise, in principle, is fairly straightforward when it comes to its sources. So it's well understood that it's sort of thermal noise and the fundamental noise related to making a quantum measurement. But that said, there's often other ambient sources of noise, for example, coming from radio stations or whatever, your cell phone, things like that. So AI could be used in principle to categorize those things.
Yeah, question here.
So is there an ideal intersection point on the graph of mass to the ratio of strength, which you theoretically think is the best spot to actually discover? And if so, are you doing a lot of simulations in software AI first before you do the validation in the physical experiment layer? Or you are running experiments in the physical environment, the detection, detectors, then coming back, and what's the latency of how many experiments, the cost and time it takes if you were to run like hundreds of experiments right now?
Yeah, so let me try to rephrase that question a little bit. So on that plot, I guess, like either on the QCD axion band or somewhere else in that parameter space, is there like a specific location of interest where you would put in more resources such as, simulations, software, to actually explore before actually doing any physical experiments?
Also, do you know theoretically at what intersectionality is the highest probability of you running experiments to get closer to a discovery?
Yeah, it's an interesting question. And I think the answer is that we genuinely don't know. So this is why all the plots I was showing are so broad in their frequency space, because there are a variety of different situations which could still provide the answer to what is the dark matter. And so at the moment, there's not really a way to go about simulating that specific, people come up with different models, right? But every time you have a model, it includes some assumptions. And so you won't know until you just directly find it, basically. So, yeah.
Yeah, and we have a, yes, I'll get to you next. We have a quite philosophical question from an online audience member, Sandy. Okay, so it's a two-part question. First of all, is dark matter kind of just a placeholder that we give because it helps in describing the observations, or it's something that actually exists and we're just trying to find it?
Yeah, that's a great question. So I didn't go into this at length during my talk, but there is an abundance of evidence that it exists. We just don't know what it is. And so the evidence is coming from our understanding of how galaxies should rotate. It's coming from our understanding of how galaxies should collide. It's coming from our understanding of gravitational lensing and the cosmic microwave anisotropy. This is the leftover light from the Big Bang. So we can sort of, look to the skies and make all these measurements, and we realize, because we understand certain physical phenomena, that there must be something missing. There's some mass that is not there. And so there's really strong evidence that the dark matter exists. We just don't know what it is yet.
Yeah. And perhaps, some of you already know that most of the matter existing in the universe is in the form of dark matter. So the follow-up question would be, if it's that abundant, why do we even have to try this hard to find it?
Yeah, that's another great question. So many good questions. So the reason why it's hard to find it is because it interacts very, very, very weakly. This is why we're not aware of it in everyday life, things like that. So it's not something you could just easily build a detector and have that interaction occur. You have to be sensitive to these extraordinarily small signals. So that's why we haven't been able to find it yet.
Thank you. Yes, over there. Yeah, do you also want to ask a second one? Okay. Okay, two questions. The first one is, why is it very hard to find or build an experiment that touches the QCD axion band or even like below it, sensitivity wise? And then the second question is like, if dark matter, as we think, it mostly just interact gravitationally, why is, like most of the models are like energy based, right?
Yeah, so for the first question, the probability of this axion converting to a photon is basically so small that that signal that we're looking for is just going to be extremely small. And so one of my slides had a number that was 10 to the minus 23 watts is the expected signal strength. And so that is a decimal point followed by 23 zeros and then a 1. So that's a very small number. So it's just, we have to build very sensitive detectors for that. And then the other question was connected with energy.
Yes.
Okay.
Yeah.
Energy models. I think how I will interpret that is, so this is this referring to maybe dark energy or just? Okay.
Yeah. Okay. So clarification: if dark matter is mostly like gravitationally interacting, like in holding galaxies together, right? Like, why are we using radios to even find those particles? Right?
Yeah, that's a really good question. So it's true that the only way that we know for sure that the axion or dark matter interacts is gravitationally, but that is gravity is already an extremely weak force. So it is tricky to use gravity to sort of do experiments like this. But we do know that there is this interaction by which the axion might convert to a photon in a magnetic field. And actually, the axion would modify the equations of electrodynamics called Maxwell's equations. And so this just turns out to be sort of an easier signal to build a detector around than something that would be gravitational. Radio technology is everywhere.
Okay, there's actually an online question kind of related from AC, who's asking, could the axion frequency also be altered by gravitational waves?
That is a question. That's a great question. I haven't thought about that very much. So could the axion, was it frequency?
Yeah, axion
frequency be altered by gravitational waves? So the axion frequency is due to the mass of the axion. But you did see there's a frequency modulation due to relative motion through the dark matter. And so I would have to think about that. That's a great question.
Hey,
that's actually more complicated than I thought. I think I'll just say I'm not sure. That's an important thing to being a scientist. When you're not sure, just admit.
Yeah, absolutely.
Yeah.
All right, over there. Oh, yeah. So the question is, when trying to detect axions, whether you are able to point your detectors in different angles to try to get signals from different places.
Mm-hmm. Yeah. So you, in fact, there are models where the axion, there's sort of these axion streams, and they're like flowing in a particular direction. So if that is actually the case, then perhaps if we're in a stream, we would have better signal detection than if we're not. However, the model for the axion that we're looking for is just sort of ambient. And so this means it's non-relativistic or not moving very much. So it's just kind of stationary. We're moving through it. And so there's not really a huge advantage to pointing your detector in any particular orientation. So yeah.
During the search for the axion signal, everything else that's interesting along
Yes. So while you're searching for Axion Dark Matter, did you find anything else, perhaps other than the radio station, that was interesting?
So, so here's the thing with the Axion searches, I didn't talk about this, but we sort of inject our own fake signals all the time. And this is to understand our detector. So we have this, we call it a blinded operation, by which people are injecting signals, and then the data analyzers are sort of studying the result, and they identify a series of candidates that might be an axion, and then we kind of go through them as a team and evaluate if that's true or not. So we always get this exciting moment where like, we found 10 axions, and then of course they were all fake injected. But okay, but so far, you know, to my knowledge, there hasn't been a signal detection where we thought, oh, maybe this is something similar to the dark matter. There are other models, but there hasn't been anything like that. There have been, you know, I think it's definitely an interesting learning experience with the quantum sensors. I mean, there's all kinds of different ideas people have about that, and having this motivation of dark matter to help drive that technology, I think that, you know, leads some, causes some interesting aha moments, I think, but yeah.
Right over there. Okay, so for axion search, would it be possible to do experiments in space so that we also don't get any of those random signals as we do on Earth?
Yeah. So in theory, I don't see a reason why you couldn't. However, currently you'd have to shoot the magnet and the dilution refrigerator into space, and that's challenging. It's maybe these days less challenging than it used to be, but you know, it requires a lot of effort. So I don't know that you would necessarily gain a very large advantage, because there are still radio signals in space. So you know, there's all these satellite communications and things. So I think you can probably do just as well if you have shielding, or if you're in a place where there's not a lot of radio frequency interference. We actually have a lot of ways to eliminate potential radio frequency interference, or RFI, I'll use that term, RFI. And because we understand what the signal shape should look like, for example. So it doesn't look like your typical radio station. It looks slightly different, it has this shape, right? So we can use that to discriminate an actual signal from noise.
Okay, probably just a couple more here. So imagine that we actually had experiments of dark matter searches in space, which would work better. I think that was kind of a follow-up question to what you just answered. Space versus ground, which, you know, not considering the money, which one would be more
like that? Yeah. Well, an interesting thing about space is that it's very cold. So maybe, you know, you have to do less shielding for your cryostat in space. But I still think it would be hard to get all those materials up there, and yeah.
Yeah, especially given how like complicated and delegated. Yeah, I saw a hand over there. Okay, can you comment maybe a little bit on where we know dark matter exists in terms of in the universe, and whether there's any localized dark matter, and if there is, whether that makes it easier to study?
Yeah, so this is one of the sort of, I want to say, confusing points about dark matter. I find it crazy to think about. So the dark matter is actually this particle like the electron or the proton, but it's really, really, really low mass. So it's so incredibly small that you know, we're not going to be aware of it, you know, here on Earth, walking around in our ordinary lives, right? So it's actually going through us and just sort of around us all the time. It's in this room. If it exists, it's in this room. That sort of, I guess, gives you a different way to think about it. And so it's not that we have to like go to another part of the galaxy to find it. It's actually, we're in a galaxy, it is here around us, but it doesn't interact very much, and it's such a small particle that it would be very hard to find. And now that said, there are many of these particles. You can have a lot of particles that are very, very low mass, but the sum total of the mass is actually substantial. And that's why it has an effect on the dynamics of galaxies, for example.
I will come back to you in a sec. So that I think actually connects to this online question very well. So well, there's also other dark matter candidates, right? For example, WIMPs, which is the weakly interacting massive particles, which are more massive and behave more like a particle compared to Axion, which will behave more like a wave. So given your talk, it sounds like Axion is a really promising model for dark matter. So does that make WIMPs less favored compared to Axion right now?
Okay, so I'm very biased here, obviously. So, you know, I think the Axion is an exciting particle because of its implications for electrodynamics and the QCD axion solving this other problem in nuclear physics, for example. That said, I have colleagues at SLAC who are looking for the WIMP, and they're doing a very good job building these sort of massive detectors to get better sensitivity. So I just want the dark matter to be found. And, you know, if it's someone else, that's still okay. I would still be just as excited. So, yeah.
Great mentality. Okay, last question. Yeah, so the question was, given what we know about Axion, how are we building detectors that are not accidentally like block out Axions that make us not being able to see the signal?
Yeah. So because the Axion is sort of as low mass as it is, it can kind of pass through a lot of everyday objects, and you know, there would be dark matter in your detector sort of no matter what. So we don't have to worry too much about that. I think the bigger concern with regard to shielding is actually keeping out the radio signals from ambient electronics and things. Yeah.
Great. Given the interest of time, let's give Chelsea another round of applause. I saw that there were so many hands, and sorry I didn't get to you, but Chelsea will be in the room until all the questions were answered. Okay, so you're welcome to stay here. And before we wrap up the event, I wanted to quickly give you a heads up of what is coming up next. So as we are wrapping up our programming for 2025, we are going to have our last public event, actually in Spanish only, called Noches Astronómicas. And that is going to be in Huli 201. We're going to have 3 very short talks about supermassive black holes, followed by a panel Q&A in about STEM careers. And in the new year, we are going to have 2 public lectures planned. One is going to be the early history of the universe, observational and theoretical cosmology, and that's going to be given by our newest faculty member, Oliver Philcox. And we're also going to have another talk focused on gravitational waves, and especially building instrumentation to detect very faint signals and a little bit of result updates of LIGO, which we haven't even featured in the past few years. And we are also planning 2 public stargazing nights, one in January and one in February, at the Stanford Student Observatory. So those are to be in person only. And if you join our mailing list, you know, you will get notified as soon as we schedule this these stargazing events, because we kind of have to wait until the weather forecast become reliable to make sure that we can announce it. So if you want to keep up with what's new with KIPAC, or want to join more events, please follow us on social media. We're also joining our mailing list And all these information will also be shared with you tomorrow in an email, also along with a survey. We would very much love your feedback regarding our public lecture, and also to hear from you what kind of topics you would like to hear in the future, so that we can gather our best speakers and try to produce those public lectures for you. This marks the end of the event. Well, thank you all for joining, and yeah, wishing everyone a great night and also happy holidays.